the formula used for quick calculations of available fault current at a transformer. Specifically, I short circuit amps equals kVA divided by volts line to line times 1.732 divided by Z%, or alternatively, I full load amps divided by Z% is not directly derived from Ohm's law. It is a simplified formula that approximates the short circuit current available at a transformer based on the transformer's kVA rating, line to line voltage, and impedance percentage, represented as Z%. Ohm's law states that the current flowing through a conductor is directly proportional to the voltage applied across it and inversely proportional to its resistance. In the context of transformers, the impedance Z represents the resistance and reactance offered by the transformer to the flow of current. The formula, I short circuit amps equals kVA divided by volts line to line times 1.732 divided by Z%, can be derived by starting with the following equation: I short circuit amps equals kVA divided by volts line to line times 100 divided by Z%. Here, kVA is the transformer's rated kVA, volts line to line is the line-to-line voltage, and Z% is the impedance percentage expressed as a percentage. The factor 1.732 is introduced to convert the line-to-line voltage from phase to neutral voltage, which is more commonly used in calculations. When a fault occurs, the impedance between the transformer and the fault location is negligible compared to the transformer's impedance. Therefore, the short-circuit current available can be approximated by dividing the transformer's kVA rating by the impedance percentage. I short-circuit amps equals kVA divided by Z%. This is equivalent to the simplified formula, with the factor 1.732 included to account for the line-to-line voltage. The formula for short-circuit current available at a transformer is a simplified approximation that uses Ohm's law indirectly by assuming that the transformer's impedance is the dominant factor in determining the available fault current. It provides a quick and convenient way to estimate the maximum current that can flow during a fault condition. In essence, it leverages the transformer's inherent characteristics to provide a rapid estimation of the potential fault current without needing to delve into complex network analysis or directly applying Ohm's law in its fundamental form. The Z% value represents the percentage of the transformer's rated voltage that must be applied to the high voltage winding to cause full load current to flow in the low voltage winding when the low voltage winding is short-circuited. This value is crucial because it reflects the transformer's ability to limit fault current. A lower Z% value indicates a lower impedance, thus a higher potential fault current. Conversely, a higher Z% signifies a higher impedance, limiting the fault current to a lower value. The 1.732 factor is the square root of 3, used in three-phase power calculations to relate line-to-line voltage to phase voltage in a balanced system. Since transformers are often connected to three-phase systems, this factor is necessary to accurately calculate the short-circuit current available on the secondary side, especially when dealing with line-to-line voltage values. The formula is a practical tool for engineers and electricians because it allows for a quick assessment of the potential fault current during system design or when evaluating the adequacy of protective devices like circuit breakers and fuses. By knowing the approximate short-circuit current available, one can select appropriate equipment that can safely interrupt the fault current, thereby preventing damage to equipment and ensuring personnel safety. To further elaborate on the application of this formula, consider its use in different scenarios. Firstly, during the initial design phase of an electrical system, engineers use this calculation to determine the necessary interrupting rating of circuit breakers. The interrupting rating is the maximum fault current that a circuit breaker can safely interrupt without failing. If the calculated short-circuit current exceeds the circuit breaker's interrupting rating, the breaker could be damaged or fail to clear the fault, leading to a potentially hazardous situation. Secondly, when adding new loads or modifying an existing electrical system, it's essential to recalculate the available fault current. Changes in the system configuration, such as adding a larger transformer or connecting additional loads, can affect the fault current levels. This recalculation ensures that the existing protective devices are still adequate to handle the potential fault currents. Thirdly, during routine maintenance and inspections. Verifying the accuracy of the transformer's nameplate data, including the kVA rating, voltage, and Z%, is crucial. Any discrepancies in these values can lead to inaccurate short-circuit current calculations, potentially compromising the safety of the electrical system. It's also important to understand the limitations of this simplified formula. It provides an approximation and doesn't account for factors such as the impedance of upstream sources, cable impedance, and the presence of motors that can contribute to fault current. For more precise calculations, especially in complex electrical systems, more sophisticated methods like point-to-point calculations or the use of software tools are necessary. These methods consider all the impedances in the fault current path, providing a more accurate assessment of the available fault current. In addition to the interrupting rating of circuit breakers, the calculated short-circuit current is also used to determine the withstand rating of electrical equipment, such as switchgear and panel boards. The withstand rating is the maximum fault current that the equipment can withstand for a specified duration without sustaining damage. Ensuring that the equipment's withstand rating exceeds the calculated short-circuit current is essential to prevent equipment failure and maintain the integrity of the electrical system. Another important aspect to consider is the impact of motor contributions to the fault current. During a fault, motors act as generators, feeding current back into the system and increasing the overall fault current level. The contribution of motors can be significant, especially in industrial facilities with a large number of motors. To account for motor contributions, engineers often use multiplication factors or detailed motor modeling techniques to estimate the additional fault current. The simplified formula does not inherently include these motor contributions. Furthermore, the impedance of cables and conductors also plays a role in limiting the fault current. Longer cable runs and smaller conductor sizes result in higher impedance, which reduces the available fault current at the point of the fault. While the simplified formula doesn't explicitly account for cable impedance, it's essential to consider its impact, especially in systems with long cable runs. In such cases, more detailed calculations that incorporate cable impedance are necessary. In practical applications, engineers often use software tools that automate the short-circuit current calculation process. These tools allow for easy modeling of complex electrical systems, including transformers, cables, motors, and other equipment. They also provide detailed reports that show the available fault current at various points in the system, helping engineers to select appropriate protective devices and ensure the safety of the electrical system. In summary, the simplified formula for calculating short-circuit current at a transformer is a valuable tool for quick estimations, but it's essential to understand its limitations and consider other factors such as motor contributions and cable impedance for more accurate assessments. Proper application of this formula, along with the use of appropriate protective devices, is crucial for ensuring the safety and reliability of electrical systems. The impedance percentage, Z%, is a crucial parameter provided by the transformer manufacturer. It represents the internal impedance of the transformer, which limits the fault current. This percentage is based on the transformer's kVA rating and voltage. For instance, a transformer with a lower Z% will allow a higher fault current to flow compared to a transformer with a higher Z%, assuming all other parameters are the same. Understanding the Z% is vital for accurate fault current calculations. The 1.732 factor, the square root of 3, is used to convert line-to-neutral voltage to line-to-line voltage in a three-phase system. In a three-phase system, the voltage between any two lines is higher than the voltage between a line and the neutral point. This factor is essential when working with three-phase power systems to ensure that the voltage values are correctly converted for accurate calculations. The formula also relies on the transformer's kVA rating, which indicates the apparent power that the transformer can deliver. The kVA rating is a product of the voltage and current and provides a measure of the transformer's capacity. Using the correct kVA rating is crucial for determining the potential fault current. It is also important to understand the concept of infinite bus assumption. This assumption simplifies the fault current calculations by assuming that the upstream source has zero impedance. In reality, the upstream source, such as the utility grid, does have impedance, but it is often much smaller than the transformer's impedance. By assuming an infinite bus, the calculations are simplified and the focus is placed on the transformer's impedance as the primary limiting factor. However, in some cases, the upstream impedance may be significant and should be considered for more accurate calculations. To further illustrate the application of the formula, let's consider a practical example. Suppose there is a 1000 kVA transformer with a line-to-line voltage of 480 volts and an impedance percentage of 5%. Using the formula, the short circuit current available can be calculated as follows: I short circuit amps equals 1000 kVA divided by 480 volts times 1.732 divided by 0.5, which equals approximately 24,055 amps. This value represents the approximate fault current that would flow if a short circuit occurred in the secondary side of the transformer. Based on this calculation, appropriate protective devices, such as circuit breakers or fuses, can be selected to safely interrupt the fault current. In addition to the interrupting rating of the protective devices, it's also important to consider their coordination. Coordination ensures that the protective device is closest to the fault trip first, minimizing the impact on the rest of the electrical system. Selective coordination involves setting the trip characteristics of the protective devices so that they operate in a coordinated manner, preventing unnecessary outages and ensuring the reliability of the system. The simplified formula is a valuable tool for estimating fault current, but it's important to recognize that it has limitations. It provides a quick approximation, but does not account for all the factors that can influence fault current levels. For more accurate and detailed calculations, especially in complex electrical systems, more sophisticated methods are necessary. These methods involve modeling the entire electrical system, including all the equipment and interconnections, and using software tools to simulate fault conditions. The results of these simulations provide a more comprehensive understanding of the fault current behavior and allow for the selection of appropriate protective devices and coordination schemes. It is also important to consider the impact of harmonic currents on the fault current calculations. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as variable frequency drives and electronic equipment. These harmonic currents can increase the overall fault current level and affect the performance of protective devices. In some cases, it may be necessary to use harmonic filters to mitigate the impact of harmonic currents on the electrical system. Furthermore, the simplified formula does not account for the effects of arc flash. Arc flash is a dangerous phenomenon that can occur during a short circuit, resulting in intense heat and pressure. The arc flash hazard is determined by the magnitude and duration of the fault current, as well as the distance from the arc. It is essential to perform an arc flash study to determine the potential arc flash hazard levels and to implement appropriate safety measures, such as personal protective equipment and arc flash rated equipment. In summary, the simplified formula for calculating short circuit current at a transformer is a useful tool for quick estimations, but it's important to understand its limitations and consider other factors, such as motor contributions, cable impedance, harmonic currents, and arc flash, for more accurate and comprehensive assessments. Proper application of this formula, along with the use of appropriate protective devices and safety measures, is crucial for ensuring the safety and reliability of electrical systems. When applying the formula, always use consistent units. The kVA should be in kVA, the voltage in volts, and the impedance as a decimal representation of the percentage. For example, if the impedance is 5%, use 0.5 in the calculation. Incorrect units will lead to significant errors in the result. Keep in mind that the calculated fault current is the maximum potential fault current. The actual fault current may be low due to factors such as arc resistance and the impedance of the fault path. However, it's always prudent to use the maximum potential fault current for selecting protective devices to ensure adequate protection. Regular review and update of the short circuit current calculations are essential, especially after any changes or modifications to the electrical system. Changes such as adding new loads, replacing transformers, or modifying the system configuration can affect the fault current levels. Keeping the calculations up to date ensures that the protective devices are still adequate and that the system remains safe and reliable. Finally, always consult with qualified electrical engineers and adhere to relevant electrical codes and standards when performing short-circuit current calculations and selecting protective devices. These professionals have the expertise and knowledge to ensure that the calculations are accurate and that the electrical system is designed and operated safely and in compliance with applicable regulations.